Okay, we are now recording, and I will turn the floor over to, this is group 17,
Yes.
to share with us your design.
Okay. Is there synchronized clocks? 3, 2, 1. Hello, and welcome to our presentation of the AutoMOM, a modularly organized microbioreactor designed for the UF Biofoundry. Our product is designed by Group 17, which consists of myself, Alexander Derivium, Julian Deutsche, Tyler Dunn, Courtney Chesser, Logan Piper, Dalton Newberry, and Stephen Lawrence. Our goal was to solve a task that required 5 functions, the immediate of which is to be able to culture cells under a stressing environment that would allow for genetic selection within laboratory environments. So the 5 things that our machine needed to be able to do was fill liquid containers and clean them autonomously, regulate temperature levels within an incubator, transport and mix unique combinations of gases to culture the cells, shake the cells to prevent them from sticking to the walls and to allow adequate mixing of the fluids within the containers, and measure optical density and fluorescence intensity levels within the cells once light was shined through them to detect how many of them were surviving. So we started, this is a general overview, but we started on the left with our 39 customer needs, which we then turned into metrics, and then we broke into subsystems. And we have constantly reiterated these subsystems to make sure they're optimized for design synergy and for optimal design, for optimal machine performance. So what is the AutoMOM? The AutoMOM is an autonomous, modularly organized microbioreactor. And the name is pretty fitting because, like a mom, it allows us to culture and grow cells. And in a stressed environment, we can genetically select them and raise them to have exactly the desired characteristics that we would want from an experiment. So I'll begin with our hedgehog concept. Our goal as a team is, because we are passionate about autonomy and modularity, we wanted to create the most thorough product in the class. And so we set out to design something that was highly customizable while being able to run itself. So I'll begin with autonomy. We have 2 main highly autonomous components. One is the incubator that can sense when an experiment is beginning or ending and will open itself to allow liquid handling to place liquids within either well plates or test tubes from which the experiment will then be run. And then it'll close itself for the duration of the experiment. Equally so, the liquid handling can swap out tools to become light handling, and it'll measure optical density when necessary, and other times it'll have a liquid dispensing tool. And even more so, there's a shaking mechanism within the incubator that turns on and off selectively as it is needed for running the experiments, which intermittently stops so that it can read optical density levels. For modularity and customizability, we have another 2 selections. One is our nozzle area. Our tool holders are highly customizable because our product can be expanded to accommodate what users want, both now and in the future. So we have 4 incubators, as you see on the right, but our design is tileable and can have up to 10, even within the same frame. And therefore, customers don't need to buy more of the product, and it encourages them to buy a single product that meets their uses, especially since this machine is already combining 5 functions that unique machines used to be required to do. Additionally, the nozzle selection, while we can have multiple tool holders for different volumes of liquids as well as for the optical density sensor, it can even be expanded to allow new types of sensing as it becomes necessary in future experiments. So I'll give you a quick run through of a use case scenario when you might be using our autobioreactor, the AutoMOM. So first, you would put in a well plate or a plate of test tubes that we've custom designed. And this works with anything from 6 wells up to 396 wells, as well as any 15 milliliter or 50 milliliter Falcon test tubes. And once you've put that in, that's your entire interaction with this for the remainder of the experiment. You would pre-program it and the machine would run the rest. It opens the incubators, fills the liquid in the device into the containers, then seals the environment, fills the gases from 5 different sources in a unique combination described by the user. Then it regulates temperature within the device using a Peltier air cooler. It from there would begin shaking the whichever container is inside at a user-specified pattern and speed. And what's highly unique about our device is that we're the only one on the market that has a fully customizable 2D pattern. You can do anything that requires a 2D pattern of shaking, which could lead way to new types of experiments. Then we will read optical density and fluorescence intensity levels. As soon as it's necessary to, the device will stop shaking and it'll read ODFI levels and then go back to resuming shaking. And finally, when the experiment's over, it will evacuate the gases so that it's returned to atmospheric conditions. It can be opened without contaminating the BSL-2 environment. And then using a 70% ethanol solution, it will empty each of the containers and flush them and let them sit so that they are clean for the next experiment without the user ever needing to intervene. And then you can program your next experiment. And from there, I'll pass it on through our next 6 subsystems that it's broken into: the incubator, the shaker, gas handling, ODFI, liquid handling, and structure, which each of my classmates will now discuss with you.
Hello, I'm Julian Deutsch. Our design utilizes individual incubation units that are able to regulate atmospheric conditions such as temperature, gas mixture levels. These units are fully autonomous, removing any human error from the experiment, as well as adding an extra level of convenience. Each module has a clear acrylic top and bottom, allowing for the optical density and fluorescence intensity calculations the user may request. These calculations are able to be performed without the disturbance of our environment, since our incubation units don't need to be opened. This adds another level of stability and overall control to the user. When adding tubes, well plates, or feeding the experiments, the lid to our incubator is opened. This is performed using a simple off-the-shelf linear actuator. By adding the linear actuator to the inside of our incubator, we're able to isolate most parts of the inside of our unit, as well as keeping a tighter seal on our lid. Next slide. The incubator solves 6 main customer needs. Need 18. Product must be capable of incubation/hibernation periods from 1 hour to 2 weeks. Our product meets this need by allowing the user to incubate for as long or as short as needed. Need 19. Product can perform culture condition closed loop control. Our design allows for complete autonomous control as well as fully enclosed conditions to remove any outside factors. Need 20. Product can culture at a temperature range from 4 to 70 degrees Celsius. Our heating and cooling is regulated by using a Peltier thermoelectric cooler, as well as a series of fans and heat sinks. This unit has proven to be the most cost-effective and simple manner of controlling our environments. Need 21. Product can culture microbes in fully enclosed compartments or vessels that are easily interchangeable and that allow for media exchange. Due to the modular unit design, the exchange of individual experiments does not affect the others. Need 24. Product uniformly heats wells/tubes to prevent condensation. Our metric was for the product to regulate a well temperature precise to plus or minus 0.5 degrees Celsius of the user inputted temperature. By heating and cooling the environment as a whole, we are able to uniformly alter the temperature of the experiments precisely within the needed range. Try to have need 2. The product must have a modular design to allow for the addition of future modules and ease of movement. We wanted our product to have the ability to be broken down into parts for ease of transportation and allow for the addition of other parts. Due to our individual incubation units, the assembly is able to be broken down into easily manageable sections to allow for the easy transportation and handling. Next slide. The analysis performed on this subsystem was determining if our Peltier thermoelectric cooler was able to regulate the temperature within the requested range. To do so, the heat flow into the unit was compared to the cooling capacity of the thermoelectric cooler. We determined that the heat flow into the incubator was nearly half of what our Peltier cooler was capable of. Because of this, we are able to assume that the temperature within our incubation units is able to be fully controlled by our Peltier thermoelectric coolers alone. Next slide. The key features of this design that sets us above our competition revolves our use of individual incubation units. Because our design is so modular, we're able to increase or decrease the number of incubation units within our system. This gives the user a range in cost and customization. This also allows the user to perform multiple experiments with individual environments. This can be extremely important in labs, especially university labs like the ones we have at UF. Next slide. The incubator subsystem has reached a technology readiness level of 3. At this point, our incubator subsystem has been analyzed analytically and is ready to move on to the next steps.
Hello everyone, my name is Logan Piper, and I'll be walking you through our shaking subsystem. The shaking subsystem accounts for the movement of the well plates and falcon tubes and can be found in each individual incubation chamber. It also allows the OD and FI sensing mechanism to reach all the individually housed microbes. Next slide. This system addresses various customer needs. Need 5 is met in the static analysis as the critical loads are well above a 1.15 factor of safety level. Regarding need 21, the tube holder allows microbe vessels to be easily interchanged, as either a falcon tube or well plate can be used. This also cultures cells in fully enclosed compartments, as the shaking system is located within each incubation chamber. Regarding need 28, the product is able to measure optical density and fluorescent intensity in all individual wells using dielectric mirrors and an open access microbe holder, allowing the micrometer to sense each plate or tube. Regarding need 31, the product is able to undergo linear, orbital, and double orbital shaking patterns with the use of a 2-motor system. And for need 32, the shaking patterns are independent for each incubation chamber, allowing the user to have different microbes undergoing different patterns. Next slide. The shaking patterns are achieved through the use of 2 cams with off-center pins. These are attached to rotating stepper motors, and the pins are constrained to a linear track, as seen on the left. When the cams rotate, the tube holder can move in both the horizontal and vertical direction. When a single motor is activated, linear motion is achieved. When they are synced to rotate together, orbital and double orbital shaking patterns can be produced at various speeds. Dielectric mirrors are used to aid in the OD and FI sensing process. The output light from the micrometer is located above this assembly and the receiving end is located underneath. For well plates, this sensing light can go directly through in a downward direction. Yet for falcon tubes, the dielectric mirrors are used to direct the light horizontally through each individual tube and then back down to the receiving end. Next slide. The rotating rods that cause linear motion were further studied using a finite element analysis. The stresses within these rods were concerning due to the slender nature and their abrupt change in diameter at each pin location. The pins are what interact with the linear holes in the base of the shaking mechanism, and this is where the highest and most critical stresses were assumed to be located. To approximate the force applied at the pin locations, a static analysis through ANSYS was conducted. To solve for the force applied to the rod, the coefficient of friction was estimated, and this was based off of the proposed contact between aluminum and aluminum surfaces before motion. The resulting force was then found. The side of the rod attached to the motor was fixed and a distributed force of 10.3 newtons was applied to the extruding pin on the opposite end. The resulting study with the finite element mesh shown below can be seen. The left image depicts the displacement and von Mises stress of the old design, and the right image is of the final redesign. The stresses found from the FEA model did not exceed the yield strength of the material. The maximum stress was approximately 1.79 MPa, and the yield stress for 6061 T6 aluminum is 276 MPa. It is important to note that the highest stresses were found with the diameter changes from the main body of the rod to the small pin. The original design on the left had a much higher stress and displacement, and for the final design on the right, the rods were shortened and widened, and fillets were added to lower the maximum stress. This allows for a factor of safety well above 1.15 and allows us to use aluminum instead of steel. Next slide. The idea to use rotary motors and cams to induce the shaking motion was inspired by electric hair trimmers. As you can see in this figure, a rotary motor was used with an off-center pin on a linear track to transform circular motion into linear motion. We gave this subsystem a technology readiness level of 5 for this reason. Next slide.
Hi there, I'm Stephen Lawrence, and I will be going over the gas handling subsystem. So this is comprised of 6 gas pressure tanks holding 5 gases, which are nitrogen, oxygen, carbon dioxide, methane, and hydrogen, with 1 empty tank. The tanks are connected to 4 incubation systems through tubing, and the gases are released into the incubators or redirected from the incubators back into a tank with the gas controller, including a mass flow meter and a compressor. The 6 tanks all have their place in the gas tank base, keeping them secure. By having 6 different tanks comprised of the 5 gases mentioned in the customer needs statement and 1 empty tank for waste gas, many different environmental conditions can be simulated for the cultures. Each tank can be used multiple times before having to be replaced, which is a key factor to creating a higher level of autonomy when interacting with our product. The tanks can easily be removed from the gas tank simply by pulling them out, and from there, the user can empty the waste tank or refill/replace the other tanks. Next slide. So here are some of our needs that are gas handling system covered. It corresponds to 6. The first one was need 5, which was have a 1.15 factor of safety based off the forces. Need 15 was to have all the materials that come into contact with cell cultures and lab chemicals be non-porous and non-reactive respectively. Need 16 was it must be able to work within the limits of the BSL2 lab space. Need 26 was the product must capture effluent gases. Now the metric here was important. It was that the microbioreactor must have the capability to capture and store the equivalent of 96.2 liters or 4 moles or more of effluent gases at normal temperature and pressure before needing to be emptied. Those would go into the empty tank. Need 27 was that it must include a gas controller that can inject and regulate the following gases. The ones I mentioned in the customer needs statement, which were nitrogen, oxygen, carbon dioxide, methane, and hydrogen. The metric we used for this one was that must be able to maintain a reliable gas injection precision of plus or minus 1 milligram. For need 35, the last one, the product must dispose and neutralize waste. And that there we go with the empty gas tank again. The metric here was that it would be capable of neutralizing and sterilizing and storing at least 1 liter of waste. Next slide. For the key features, we found many in the gas handling subsystem. The first one was that it is highly customizable. As mentioned before, 6 tanks are used, 1 for each gas mentioned in the customer needs statement and 1 for the waste gas. The waste gas is able to pull from the incubator and kind of clear the air to be able to proceed with another gas environment simulation. Number 2 is that it is precise. The mass flow meter detects how much gas enters the containers, allowing for environmental conditions to be created. Another one is that the system is autonomous. As you will see throughout our product and throughout this analysis in the next slide, multiple rounds of incubation can be run without having to replace the gas tanks right away. The gas controller is connected to the electronic interface subsystem so that the user can have automatic and computer run gas injections and retractions. Now, finally, with size. With lots of tanks and incubators, it was difficult to be able to fit everything into the full assembly, but we definitely accomplished that here. We are able to fit the entire gas handling system within the full assembly, which is a benefit both for speed and for overall product appeal. Next slide, please. So for our analysis, we wanted to know how long our gas tanks would last given an extreme scenario. So the 2 temperature extremes specified in the customer needs statement were used to measure how much oxygen would have to be retracted from the oxygen pressure tank if the entire incubator needed to be filled with only oxygen at 1 bar of pressure. To determine this, the density of oxygen at these temperatures and pressure was found in the inverse of this was multiplied with the mass of the oxygen specified within the pressure tank that we pulled from McMaster to determine the volume of oxygen in the tank. An approximate volume of the incubator was also determined. And then the last step was finally, the volume of the tank was divided by the volume of 1 incubator to determine how many times the tank could fill the incubator with oxygen up to 1 bar pressure. The results were that 4 rounds could be run at the 4°C temperature, while 5 could be run at the 70°C temperature. Next slide, please. For our technology readiness level, the gas handling subsystem reached a TRL of 3 because it could be analyzed analytically and is able to be moved on to the next steps.
Hello, I'm Tyler Dunn, and I will be going over the AutoMOM's OD-FI subsystem. The main design purpose of this subsystem is to monitor and measure both optical density and fluorescent intensity. This was done in our design by using this sensor arm. The excitation device is on the sensor arm and is placed below each incubator. The optical density sensor is actually placed above on the nozzle positioning system, allowing us to measure the optical density and fluorescent intensity for each well in a well plate or each tube in a rack of test tubes. Next slide. The AutoMOM's OD-FI subsystem covers 3 of the customer needs. To satisfy need 28, our metric was that the OD600 value, essentially the accuracy of the optical density values, was in the range of 0.8 to 1.2. Our product's dark machine interior ensures that no ambient light will affect the values, and as such, our device will be well in that range of values. To fulfill need 29, we compared the advantages of each and decided to use a monochromator light. For need 30, we proved that our device would solve this need in our analysis shown in the next slide. Next slide. To ensure that we fulfilled the customer need on light intensity, we did an analysis. To calculate our light intensity, we found the wattage of the LED assembly. Then we took the distance from the light source to the sensor and divided it in half to get the radius. Final equation we used is taking the wattage and dividing it by 4 pi r squared, and then also factored in the 640 times to the negative 9, since it is at 640 nanometers. This resulted in 1.28 kilowatts per centimeter squared, which is greater than the customer need value of 1 kilowatt per centimeter squared. Next slide. The AutoMOM's ODFI subsystem has several key features. The optical density sensor was actually not shown in previous assemblies because it's, like I said, it is placed on top with the nozzle positioning subsystem. The bottom light assembly and the top nozzle positioning assembly both must be positioned in a line to achieve the desired values. The key electronic for the light assembly is that bottom excitation device. On that device is where our LEDs are placed, which will release the light directly to the optical density sensor when properly aligned. An additional key feature of the AutoMOM, as I stated earlier when going over the needs, is that the entire machine will have a dark machine interior. This ensures that ambient light is not going to be altering our ODFI readings, and the result our product gets is accurate. Finally, this design is a modified custom assembly. Many current products on the market simply use an entire off-the-shelf ODFI assembly. While the sensors in our design make the system still expensive, it is much cheaper than simply buying the entire subsystem off the shelf. Next slide. Our subsystem being a modified custom assembly rather than being off the shelf was an idea that was influenced by an already existing open assembly microbioreactor pictured above. Their device has been tested and works in relevant conditions. Since we have seen the key components of what would become our subsystem tested and used in relevant conditions, we believe that this design has a technology readiness factor of 5. Next slide.
Thanks, Tyler. I'm Courtney Chesser, and I'll be explaining our liquid handling subsystem to you all. This is our detailed rendering of the full subsystem assembly, depicting the details of the modified OTS guide rails and electronic pipetter. Next slide. The exploded view shows how the pipetter is mounted to the positioning function of the liquid handling structure. 3 guide rails are used in the design to ensure a range of motion in 3 directions. 3-dimensional motion is important to the subsystem, so all individual wells can be processed with accuracy and in a window of 6.5 minutes, leading to the customer needs fulfilled by the subsystem. Next slide. Liquid handling covers 6 customer requirements. The purpose of the subsystem is to complete customer need 25, which is automated addition and subtraction of fluid into wells. Materials of liquid handling are non-porous and non-reactive, as they have the possibility of coming into contact with cultures. Quick dispensing is recognized by requirements of a 300 microliter per second minimum dispensing rate without creating aerosols, and again, the capability of filling a 384 well plate in 6.5 minutes. The electronic pipetter was chosen because it meets all of these needs, plus achieving a range of volumes with precision and accuracy. Next slide, please. These values are given by the vendor of the electronic pipetter and are displayed with the table on the right-hand side. The flow rate of the pipetter was not specified by the vendor and is therefore calculated on the left using a fluids analysis with a result of 400 microliters per second, which is above the required 300. Next slide. Weighing many options for liquid handling, the electronic pipetter best met the customer's requirements. We are really excited to be incorporating this, as the alternatives would have required many more parts. It provides a range of volumes with accuracy levels that could not have been assured with other designs. It also minimizes waste without letting any escape. The entire liquid handling assembly is made to fit into the upper portion of the AutoMOM and connects to the user interface to be an automated process. Autonomous liquid handling designs exist, but are more expensive. Creating our own design with open source stepper motor guide rails assemblies is a much cheaper option and better fits the customer's requirements. Next slide, please. So an example of the autonomous liquid handling design is the OpenTorrens robot. It has many of the same features of our design and shows the similar technology in a relative environment, which leads to a technology readiness level of 5. Next slide.
Hello, I'm Dalton Newberry. I'll begin with an overview of the structure subsystem. The main structural framing of the subsystem is made of 80-20, We chose 80/20 as it is surprisingly the cheapest option, even cheaper than square tubing and other common structural materials. Additionally, it is easy to assemble with minimal know-how and common tools. It can be completely taken apart if the system needs to be moved or worked on, which would not have been possible if the frame was welded. Two materials were chosen to encase the AutoMOM: sheet metal and ABS. The floor of the product is made of corrosion-resistant 3003 aluminum sheet. This material can stand up to chemicals, which is important in the event that chemicals are spilled and make it to the bottom of the machine. The panels that make up the sides and the bottom of the machine are made of ABS. ABS is resistant to bleach, chlorine, hydrochloric acid, isopropyl alcohol, and other common lab chemicals that it may come into contact with. Additionally, the ABS sheets are opaque, preventing ambient light from entering the machine and causing inaccurate optical density and fluorescence intensity readings. ABS also has a smooth texture that makes for a sleek design. Next slide. For the organization of the components within the structure, the focus was placed on the incubators, which were placed in the center. Below the incubators is the ODFI subsystem, and above is the nozzle positioning subsystem. The setup was possible because of the clear top and bottom of the incubators. The liquid containers were placed directly next to the incubators for easy access by the nozzle positioning subsystem. Additionally, the gas canisters were housed directly next to the incubators as opposed to outside of the machine, reducing the length of tubing and creating a more compact product. Next slide. One of the most important customer needs related to the structure subsystem states that the machine must fit inside a research facility on a benchtop. Our design weighs a total of 290 pounds, far below the capacity of 1,500 pounds for laboratory benchtops. Additionally, when assembled, the product is 28.25 inches wide. The AutoMOM is to be used in a BSL-2 lab space, which must have self-closing doors. As self-closing laboratory doors must be at least 36 inches wide, our product can easily fit. To ensure that the product is accessible to a person of average build, we specified that the tallest point on the machine must be no more than 48 inches from the base. The AutoMOM is 38 inches tall. The system can be assembled with minimal know-how, as it only requires screwdrivers and wrenches, both commonly used tools that are easily obtained and used. Need 16 states that the machine must meet the requirements to work in a BSL-2 lab space. These type of lab spaces are used to study moderate risk infectious diseases, and the main concern is preventing aerosols from contaminating the air. This is prevented by having a closed outer structure while performing liquid handling and experimentation. Additionally, our incubators are fully enclosed, minimizing the risk of aerosols further. Next slide. There are a couple of key features of the structure subsystem that work synergistically with others. The first is the fact that while the machine is running, it is fully shut off from ambient light. This allows more accurate OD and FI readings. The second key feature is the compact design that revolves around the incubators. This allows the liquid and light handling subsystems to have a reduced travel distance and make the product more compact overall. Our structures, next slide. Our structure subsystem is at a technology readiness level of 6. As seen here in the pictures, 80/20 structures are being used to build machines that aid in medical research. A representative of the deliverable is being demonstrated in relevant environments. Next slide.
Okay, so the overall cost of our product fits within our $10,000 budget. We achieved a product cost of $9,192 after doing 2 full iterations of the design. We have several competitive advantages, the primary of which is that we have the most highly customizable design available on the market. We have, but most importantly, that we have most thoroughly vetted our product more than any other team. We consulted an electrical engineer to make sure that all of our motors and actuators, as well as our liquid handling, could be handled by the Raspberry Pi and the controller that are within our system. And we can take all data measurements through it as well. We also can accommodate any unique shaking pattern or well-sized plate and the 15 milliliter and 50 milliliter tubes. Finally, so one last look at the AutoMOM. It is autonomous, modular, customizable, and ready to combine several previously existing functions from separate devices into one, therefore saving you lab time and money and effort on personnel. Thank you for attending our presentation. We've been Group 17 with the AutoMOM.
All right, great. Thank you for your presentation. We've got only about 8 minutes, so let's open the floor to questions.
Yeah, I'll go. The FEM you were showing of your little cam deal on your motors for the shaker system. I noticed you had a pretty high stress down at the root of that. I don't know for sure, but I suspect a lot of that is somewhat artificial, given the density of your mesh. I would recommend going to something like Peterson's. I'm almost positive Peterson's has a case for this. But that aside, you mentioned that you had what 179 megapascals of stress versus a yield stress on the order of what, like 250. I'm sorry, I don't know it for most materials in metric. That's a pretty substantial fraction of yield stress, and I'm wondering about fatigue and whether fatigue is going to be a concern at that stress level.
Yeah, so the stress when we did the redesign was pretty low. I think the fraction of the yield stress was, I mean, it was almost like one of 100, 1 in 100, 1 in 200 of the yield stress. So we figured that.
Okay, I may have my units wrong.
Yeah, we were actually really low. The yield I think the yield stress on there is 1 point. Let me find it in my notes. It was 1.79 MPa on the maximum stress level that we found in the design, and the actual yield stress was 276 MPa. So it was really, really small with the new redesign, which is significantly shorter. So we decided that the fatigue wouldn't be a problem with that because it was really, really small. But we could conduct an extra study on the fatigue just to be sure. But we with the redesign, we figured that it would be okay.
Okay, yeah, I think I just had a units error on my part.
You're good, but I appreciate the insight.
Just to kind of piggyback on that question, this pin, the plate with the slots in it that go in the two different directions, what is that plate made out of?
Aluminum, I believe.
So they're both aluminum?
Yes.
Okay. Okay. Because I was thinking if the other material was steel, so it may not be an issue from a stress standpoint, but from a wear standpoint, I wonder how long that pin would last, you know.
Yeah, we figured that aluminum on aluminum was better wear than steel on aluminum. That's why we really wanted to do the redesign to get the lower stress. So that was definitely something that we took into consideration when we were trying to change the material to aluminum on aluminum. But
yeah,
yes.
We also minimized the amount of friction that would be on the parts since it's sliding on Delrin rails, which have a very low friction. It reduces the amount of actual force on the pin. So hopefully that kind of counteracts the amount of friction that the parts experience by colliding with one another.
I'm going to hop in here for a second. So you guys have got those 6 bottles, 5 contain processed gas and 1 is a waste container. And we didn't ask you to do it, so I understand the reason, but I don't see any like connections.
They're hidden for clarity, but let me fast forward a little bit. We do have sort of a cross section to give you an idea of where the electronics are, and I can describe for you. Sorry, how
I'm not worried about the electronics. I'm worried about the gas connections, like the hoses from the bottles into the chambers. And my big concern is, well, you've got 4 of those environmental chambers there. So how do you split up the gas? And then I think I also heard you say that you can add even more, right up to 8, I think is the number I heard. So this starts to look like kind of a rat's nest pretty quickly. So I wonder if you could comment on how you do the plumbing.
So the way we do it is kind of interesting. We've got electronic solenoid valves, which have 5 inputs, each for the source gases, and then that goes to a single output, which goes into the mass flow reader. So we know exactly how much is going into our machine, and we're only selecting 1 at a time. Then from there, we go into a second solenoid valve, which branches back out into 4 separate tubes that goes into each of the incubators. So the gases are selected for, go through mass flow reader, then go into the incubator. Through the same nozzle, the solenoid valve that we're using is a 5-to-2. So since there are 4 incubators on one side, there are 2 outlets on the other side. One is the mass flow reader, and the other is this handheld airbrush compressor. And so what would happen is we'd select for the airbrush compressor, and it would suck the gases that are inside the incubator out and into our waste tank.
What pressures are you anticipating your tanks being at?
I don't remember off the top of my head, but the idea is that we're buying them fully filled so that the pressure gradient is always higher in the tank than in the incubator, and it forces the flow of gas into the incubator. And then even though the compressor isn't that strong, it's not necessary for it to be, because again, you'll have a higher a higher pressure inside the incubator than in the waste tank. And so the only tank that the most frequently needed to be empty tank would be the waste one, but the other 5 would be replaceable once every 5 experiments.
So
I actually covered.
You're going to vent an incubator at something like 1 atmosphere into your waste tank?
I think the expectation is that the pressure is a little bit higher, because the idea is that once we're evacuating the gas, we're also flooding it with normal atmospheric conditions. So the pressure would increase as we're sucking the new gas out, and that should force the gradient in the direction of the compressor.
So you're going to vent your incubator to the atmosphere, pump gas out until you're satisfied that whatever's in there is gone, and then start filling with your other 5 gases again. I guess my concern is, if you're going to pump into a waste tank at any sort of pressure, right, that you're going to need a somewhat powerful pump to do that. And I'm worried that if you're going to suck a vacuum really quick and potentially collapse your system.
Okay, yeah. So one of the things we try to avoid is, as we're emptying the incubator, we wanted to avoid, because it would kill the creating a vacuum in any specific scenario, but we won't be able to fill up the waste tank to a high pressure. Does that answer your question?
Yeah, I think so.
Going back to something that you said earlier too, like how pressurized were the tanks going to be? In McMaster, they said standard temperature and pressure, a 3-inch diameter oxygen cylinder with a 10-inch height had 1.4 ounces of oxygen, and you can figure out with the density of oxygen under those temperatures and pressures, like how much it would be. Yeah.
In our next presentation.
Okay.
Any other question?
Any other questions? I may need to. We're kind of at the end of time. I'm still not, kind of to follow up on what Tom was saying, not entirely sure I understand the evacuation system, but I think the questions that I want to ask are probably longer than we have time for. So maybe we're going to meet anyway, right, next week to talk about administrative stuff. So okay, so I can ask you guys then. Are there any other questions from the panel?
Dr. Trump, not a question, but more of a comment.
Yeah.
I commend the team from a presentation standpoint. I think every member of this team was well spoken. As far as the volume of their presentation was good, the speed was good, and they came across to me as very confident as they were going through their presentation. So from that standpoint, well done. Good job.
Thank you very much. We appreciate it.
Thank you.
Thank you.
All right.
Thank you all for attending.
All right. So on that note, let me stop recording.